Hi, everyone. I'm Alex. And let's talk about sharding. A couple words about myself. I'm one of the founders of Near. I will talk about Near in a second. Before Near, I was working for a company called MemSQL. It's a sharded database, which is going to be very relevant for this talk. I was the first engineer at MemSQL. I joined when it was a very small company, 3 people in a Pomeranian. I left when it was a multi-million ARR company with 150 employees. Before MemSQL, a decade ago, I was working for a company called Microsoft. And before Microsoft, I was participating in ASM ICPC, which is a world championship in competitive programming, which happens every year, where I got a gold medal. We started Near last year in August. Near protocol is a layer 1 protocol, so it's in the same space as Ethereum, for example, with the primary focus of building a very developer and user-friendly system. So the goal, the big vision is that if a developer from outside of the blockchain comes into the blockchain space and wants to build an application, it should be as easy as building a Node.js application. They shouldn't have to understand all the intricacies of Validity, and they should have good developer-friendly debugging tools, and like ecosystem should be built around them. And it's when a user who never used blockchain comes into ecosystem and try to use an application built for a blockchain protocol, it should be as easy as using some Web2 application. They shouldn't install any wallets, MetaMask. They shouldn't understand gas fees. They shouldn't understand public key security. And Near, being a blockchain built in 2019, is also scalable blockchain. That's what the entire presentation is going to be about. And when people build scalable blockchains, they usually do it in one of the 2 ways. One way is to optimize every single layer of a blockchain, but still have every node process every transaction. Right? If you think of Solana, Algorand, Thunder, Space Mesh, they all do some sort of that. Right? They try to make every node to be significantly more powerful and like they optimize every layer so that at the end of the day you can process not 7, not 12, but hundreds or thousands of transactions. Or alternatively, you split the work. You say, well, let's not have everyone process every transaction, let's split it in some way. And so that's what is called sharding. That's what we're going to be talking about today. OK. And a couple more things about Near. We call it ICPC coin. That's the way to contrast it with a variety of professor coins. Among 22 people at Near, 10 people, not 10 people, but we have 10 ICPC finals. We have 4 gold medals. And everybody has a lot of background in the industry. Everybody comes from industry. So everybody have between 5 and 10 years of experience at Facebook, Google. Few people come from MemSQL. Cool. So with that being said, let's actually talk about sharding. How does sharding work? So this is a blockchain. That's how Ethereum works today, how Bitcoin works. And let's say this blockchain, let's say we're not optimizing it in any way, so it can process 12 transactions per second. And so the general idea of sharding is if we have 3 of such blockchains, now we can process 36 transactions per second. Right? And so those chains, they can be application specific. This is what Polkadot is doing, or this is what Cosmos is doing, where every chain is dedicated to a particular application. Or they can be general purpose chains. This is what Ethereum Serenity or Near is building, with the idea that you just separate work among multiple chains, but it is transparent from the user. They don't have to think which shard their application is executing on. Sharding has multiple big problems. That's what we're going to be discussing. One of them is that the general idea when you build sharding is that you don't want everyone to validate every single block in every single shard. Otherwise, you're not really benefiting much from sharding. Right? I mean, it doesn't help if it's multiple chains if you still have to do exactly as much work to get up to speed. And so you need to have some level, you need to have some heuristic which will tell you that the chain you're observing is actually valid without going all the way through the history and validating every block in a shard which you have not been validating. And the general idea, which is used in many, both sharded and not sharded blockchains today that use proof of stake, is to rely on the following idea, that if you have some global set of validators for which you assume that it has less than some percentage of malicious actors. Let's say you assume that the global set of validators has less than 20% of malicious actors. Then if you randomly sample a smaller set of validators, you can estimate the probability that you will have more than some other percentage of malicious actors in the sample. So for example, if your global population is on the order of 10,000 validators and you sample 100 of them, and you assume that the global population has less than 20% of malicious actors, you can estimate what is the probability that the sample has more than 33%. And like the actual number is going to be so small, you can presume it's 0. Right, and so then you can say, well, that means that if I run some sort of BFT consensus with that sample of validators, it will be safe and live. Right, and then from there, again, I will use BFT consensus as an example here. If you, as a light client or some participant in the chain, you fetch a block from the current set of validators, the latest sample of the validators, and you see there's 2/3 plus 1 signatures on that block, you know that that set of validators actually did sign on the block because you assume that there's less than 1/3 of them who is malicious. And those validators, in turn, before that, these validators, they fetched it from the previous set of validators, and by the same assumption, that set of validators, because that set of validators was not malicious, signed on the block. And by induction, you can go all the way back to the genesis block. And so by induction, you know that the block you fetched is actually a block on the canonical correct chain, and you don't have to go all the way back and validate all the blocks. The problem with this approach is that these validators, they need to change. It cannot be, you cannot have the same set of validators validating every block, because over time, if the set of validators, if you sample it once and it's fixed, at some point they will figure out that they can actually collude, right? Over time they will figure out that there's maybe a way for them to benefit more if they cooperate in some way and break the system. Or like some adaptive adversary can reach out to them, bribe them in some way. So you do want to rotate them every now and then. And as you rotate them, the problem is that if every shard is as busy as Ethereum 1.0 today, then the loading state, you need the state to validate the shards. Then loading state takes time, right? So if it takes the same amount of time as it gets today to spin up a Geth node, that's on the order of multiple hours to a couple days. That means that the validators cannot rotate more frequently than that, right? So they will be rotating at least, in the very best case, every couple days, probably every week, right? And then we can get back to the same problem, that 1 week is probably enough for an adaptive adversary to find the people who were sampled. So even if your initial distribution only had 20% malicious actors, and you sampled, let's say 100 or some number of them, and you know that that sample had less than 33% of malicious actors, within 1 week, someone can find those people, identify them, and bribe them in some way, right? And that is very likely because, first of all, people who validate blockchain, usually their primary objective is maximizing profits, right? If you go to Cosmos, to their Polkadot, or any proof of stake system, the validators, that's, for many of them, that's their primary business model, the rewards from the validation, right? They're seeking money. Very few of them work there and validate because they want to maximize the security of the system. And the most common solution to this problem of, first actually, let's see how bad it is. So what happens if someone actually goes ahead and manages to corrupt a large percentage of people in a particular shard? They can execute this attack, which is called an invalid state transition. And the idea of the attack is the following. So let's say in the shard 1, we did corrupt 2/3 plus 1 of validators. What we're going to do is we're going to create a block which is invalid, in the sense that that block just doesn't properly apply, like it has a set of transactions, and the final state is not what you would actually get if you apply those transactions to the original state. So an example would be a block in which at the end of the block I get 1 million ETH, but there's no transaction which sends me any ETH. Right, so it's a completely invalid block, something that you would immediately discard if you're validating the chain. But the validators in the chain, they will sign the block, so it has the 2/3 plus 1 signatures, right? And they might create a couple more blocks on top of it. The validators in the second shard, they do not have an ability to validate every block in every other shard. So they use that heuristic that we discussed. They receive the block C, it has 2/3 plus 1 signatures, it's built on top of block B, it has 2/3 plus 1 signatures, they presume it's correct, right? And so you can execute some cross-shard transaction which will send money from shard 1 to shard 2, and that money was minted out of thin air, right? So how do we fight it? The most common approach is called fisherman. This is what Polkadot is using, this is what many sharded blockchains use today, with the idea that for as long as you have at least one person who is honest, it could be one of the validators if you didn't manage to corrupt 100% of them, or it could be someone completely external. It could be just a person who cares about the shard and runs a full node. And that person, because they do have a state and they validate the chain, they will see that the block is invalid. And so what they will do is they will, on the protocol level, they will create a proof, a cryptographic proof that there's an invalid block. And they will broadcast that proof in some way. So in this particular example, let's say that they send a proof to the shard 2. And the idea here is that the shard 2, after receiving block C, they will wait for some period of time before the challenge arrives, right? Because it takes time to spot the problem, it takes time to create the challenge, it takes time to broadcast it. So we need to allow some time, ideally order of magnitude bigger than the actual block production time or cross-shard transaction time to receive the challenge. And the first problem with the fisherman is it affects finality in a very bad way, right? If there is a cross-shard transaction, which has one part that executes on shard 1 and another one that executes on shard 2, then after shard 2 learns about the first part being executed, they have to wait for the entire challenge period before they can apply the second part. And if the challenge period is 1 hour, now we get cross-shard transactions which take on the order of 1 hour. That's very slow. And so more common approach today is instead to do the following. When shard 1, so let's say invalid state transition occurred here, and then as of here, we initiate a cross-shard transaction. The more common approach is to immediately apply the second step of the transaction on the shard 2 optimistically. Because in the optimistic case, shard 1 is not corrupted. Corruption is very expensive. It is expected to happen extremely infrequently. There's many protocols that assume it never happens, right? And then if it does happen that this block was invalid and there's a phishing attempt, then we just unroll both of the chains, right? We just say, well, this block was based on an invalid assumption that this transaction was valid, so this block also becomes invalid, and the second shard also unrolls, right? It still affects finality in a negative way, because it is still the case that as a user, I will have to wait here for the challenge period. But in an optimistic case, you know, if my transaction is pretty small, I probably don't really think that someone will go ahead and like go above and beyond to unroll it. But second of all, if I'm validating both shards, if I'm a validator who have full nodes on both shard 1 and shard 2, I will actually know that there's going to be no fisherman challenge. So in this case, for me, the cross-shard transaction is instantaneous. There's another problem, which is in this example, in shard 1, when it is corrupted, we have 2/3 of these guys corrupted. They created block B. They never actually sent block B to shard 2. We cannot send full blocks between the shards. It's way too much network, right? So in reality, what they will do is they will send a header of the block to shard 2, and they will send some Merkle proof that says that the cross-shard transaction that we want to execute is actually valid. And what they can do is they can actually never reveal the full block to anyone. Right? They will create a full block. They will send the header to everyone who cares, to all the light clients, to all the other shards, with all the proofs. But the full block, they will keep hidden. And so the fisherman has no way to actually create a challenge or even to learn that there was an invalid block because the block is not available. Right? And so we need some way for the shard 2 people, for the shard 2 validators, when they receive block C, they need some way to be certain that blocks A, B, C, and all the blocks in the past, that they're available to the people who can challenge. They need to have that certainty. And the problem is that you cannot prove cryptographically that some data is unavailable because it is indistinguishable. Like if there are 2 people and one of them claims that one person claims that the second person doesn't send data, it is indistinguishable if the second person actually doesn't send data or if the first person received data and now just says they never received data. There's no way to distinguish those 2 situations. But you can prove that data is available, obviously, right? And so I'm going to talk about 2 approaches to data availability. One is approach that Ethereum Serenity uses. The idea of the approach is that while validators are rotating very infrequently, to ensure data availability, you actually don't need to have state. And so you can have a separate set of people who rotates very frequently, like as frequently as maybe like every few seconds. And so all they do is they rotate into shard 1, they jump into shard 1, they try to download the block, they test the block is available, and then they go jump to the next shard, then load the next block in that shard, and they're just jumping very frequently, right? And corrupting them is very hard because you only have 15 seconds to identify them, right? And so if you're concealing a block, then the validators will jump into your shard, they will see that the block is not available, they will not attest to its existence. All other shards now have, they will be pretty suspicious of any header that comes from that shard, right? And I'm going to talk about Polkadot approach, which is in Polkadot, the validators of every parachain, of every shard, they all collectively also validate a global chain called relay chain. And the idea is that if you're a parachain collator, the person who creates blocks on the parachain, you will create a parachain block, and that block you will distribute it to the validators of the parachain, who also happen to be a subset of the global relay chain validators. And that block, it will be split into 2f+1, where f is some constant, such that 3f+1 is the total number of validators in the entire system. So you split into 2f+1 little parts. Actually, f+1, that's a misspelling. You split into f+1 little parts, and then you compute an erasure code so that you have a total of 3 f+1 parts, such that any f+1 is sufficient to reconstruct. And you send one little part to every validator on the relay chain in the global system. Because parts are very small, the total overhead of the network is actually not as high. On average, every validator will receive 3 multiplied by size of a single block data per time step per block of the relay chain. But now, for as long as 2/3 + 1, 2f + 1 of the global set of validators say that they saw something, at least f + 1 of them, by assumption, saw it, right? And so you can reconstruct the block. Like you can just go to each of those validators, you can pull their little parts, and you can reconstruct it. So you know that if 2f + 1 people signed on the relay chain block, that means that any parachain that built up to that point, all those blocks are available, right? Okay. And so now that we have data availability sort of working, Fisherman still has some undesirable properties. One of them is that you do rely on the fact that there's someone still available. But the second one is that when phishing attempt happens, you still unroll the chain. It is very undesirable, right? Because that affects your finality. Now you cannot, ideally you would want to see a block and be reasonably certain that the block will not get unrolled. And so there's this concept of stateless validation, which is used in many modern blockchains. Ethereum Serenity uses stateless validation, Polkadot uses stateless validation, Near uses stateless validation, with the idea that if you remember that idea of the second set of validators jumping very quickly between shards and attesting that data is available. So the next step, the next natural step would be to say, well, if they're already jumping to attest that data is available, they're already receiving the block, let's get one step further and let's also send them sufficient information for them to validate the block, right? They don't need the whole state of the entire shard, right? Because the transactions in the block, they only affect part of the state. So you will send them the block, you will send them all the state that was affected by the transactions in the block, and you will send them Merkle proofs of those transactions, right? And so they will be able to say, yes, that part of the state corresponds to the state root I saw as of last finalized block. And if I use that state that was sent to me and apply transactions that are in the block, I actually do get the state as of after the block, the next state root. And so this way, you can have people who do not have the state of the shard validate blocks in every shard, right? And so they can jump relatively frequently. Stateless validation has its own set of issues. One of the biggest ones is that those proofs are very expensive, right? If you have a payment transaction in itself is on the order of 100 bytes, right? There's a from whom to whom and a signature. While with the proofs, now you have a Merkle proof which has like 32 to 48 or like even more hashes where every hash is 32 bytes, right? So the transactions become significantly more expensive. And so network overhead increases, right? And if you're network bound, then if you do manage to send those huge blocks with proofs every block, that means that if you were not doing that and you're network bound, that means you could have had actually bigger blocks and higher TPS, right? So you're sacrificing something there. Okay. I will skip the part about Nightshade. Unfortunately, I'm running out of time. But if you do want to know how Near is building, we build on top of all the ideas I was just discussing and a little more than that. We have a paper published. It's near.ai/Nightshade. Go check it out. Cool. Now, to wrap it up, question to everyone. Raise your hand if you saw at least one episode of Whiteboard series. That's very few. OK, cool. That's great. So Whiteboard series is this YouTube video blog we have where we invite other protocols to the and in front of the whiteboard for 1 hour we talk about their technology and nothing else. So we go very deep. And we talk to Ethereum, Polkadot, Cosmos, multiple plasma chains, many layer 2 solutions. There's 25 episodes total, MakerDAO. So go check it out. It's near.ai/WBS, whiteboard series. We have a beta program. If you're building an application and you want your application to be actually used by someone, you want people to be able to go ahead and interact with it, check out the beta program. It's near.ai/beta. If you want to learn more, it's near.org is our website. And we like vanity metrics, so please follow us on Twitter @nearprotocol. Thank you. Unfortunately, there's no time for Q&A. I'm 3 seconds away from leaving from here, but if you have any questions, find me. I'm going to be on the venue. Thank you.